Okay. Well, so what do we want to do with this discussion? First of all, I just want to say very few words about our four panelists, who probably everybody in the audience know, because they've all been doing seminal contributions, but at the core of quantum theory and quantum foundations and at its various boundaries. So in particular, I would say Wayne Myrvold from the University of Western Ontario, working more at the boundary between quantum physics and philosophy of science. Paweł, many contributions, but in particular, we highlight those at the boundaries between the quantum and the classical world. Ivette from the University of Southampton, again, many contributions, but in particular, those at the boundary with relativity and quantum field theory through relativistic quantum information. And last but not least, Rob Spekkens, Perimeter Institute, again, several contributions, including in particular those at the boundary with theories beyond quantum theory, generalized probabilistic theories. So we have seen a little bit of these various aspects in the today's talks. And I think now we just want to have a chat around to see what is your take on the status of quantum foundations research at the moment, and what can be future directions stemming from your work or work from others, and in particular, what can motivate younger people in the audience to continue working along these lines. So first question I want to ask you, and I'll give you each 5 minutes to answer this question, so to set up your points of view and on this is, it's just the following question. In your opinion, does quantum mechanics contain everything it needs to describe our classical reality, or does it need some modification? Let me start with Ivette.
Yeah, hi, thank you very much, Gerardo, for this invitation. I'm really excited to be here and also to see people like Wayne and Rob and yeah, old friends. That's really nice to have this chat. So, well, like you said, what I've been working more is like the frontier with gravity, right? So in terms of the transition to the classical world, I guess that's also related to the transition into scales in which relativistic effects also become relevant, and so on. So I guess a good way to look at it is asking the question: should we quantize gravity, or should we gravitize quantum mechanics? So this would be like, should we keep the foundations of quantum mechanics and change relativity somehow to fit in with it? Or should we do the opposite and keep the foundations of general relativity and change quantum mechanics? And also, quantizing gravity is sort of keeping quantum mechanics and changing general relativity, and quantizing and gravitizing quantum mechanics would be the other way around. And I think that ultimately it's going to be experiments which tell us what, and I mean, most probably we will have to change both. But I think what we want to get from experiments is which ones are the principles that we should keep and which ones we can sort of modify and live without. So I think that's the big question, at least in that boundary. And that will, I guess, answer questions also in the transition to the classical world, because one of the important questions to answer is, does gravity collapse the wave function, for example? So when you're looking at the interplay of gravity with quantum mechanics, if that happens, like Roger Penrose predicts, then that would be like a good way of explaining the transition between the quantum world to the classical world. But well, we do need to do something about how these theories interplay, because quantum mechanics obeys Galilean transformations, and general relativity, the equations are invariant until Lorentz transformations, so they treat space and time in a different way. So in quantum mechanics, in the Schrödinger equation, it has one derivative in time and two in space. And one we treat as a parameter, time, and positions we quantize. So space and time are not interchangeable. Whereas in general relativity, we understand that space and time are not so different and they belong together in a higher dimensional object, which is space-time. But the important thing there that they're treated as in an equal footing. So obviously there's something that must be changed there to explain phenomena at the interplay of quantum mechanics and general relativity. But as I said, I insist, I think we're going to figure out more from experiments.
Thank you.
That would be my take at that.
Well, this is what has happened in history. Every time it was experiments which eventually told us that we needed a new theory because things started not to add up anymore.
Yeah.
Right. Yes. Wayne, what is your take on this?
Okay, the question that you were posing is, does quantum mechanics contain everything it needs to describe the quantum to classical transition? Well, I don't mean to sound like a stereotypical philosopher and say, well, what do we mean by this and stuff like that? But I do think the answer is, well, it depends on what you want from a quantum to classical transition and on what you mean by quantum mechanics. And let me explain what I mean by that. So one way of approaching the quantum classical transition is by investigation of phase space functions like the Wigner quasi-distribution, which we had some talk of in an earlier talk today. And what you get in an appropriate limit is something that acts at least approximately like a probability distribution on a classical phase space. Okay. Is that it? Have we gotten classical physics out of quantum physics there? Because we do have the resources within quantum physics to get that. Well, I can see someone saying, well, hold it, wait, that's not what I wanted. I didn't want a probability distribution over classical states. I wanted a picture of the world like the classical picture of the world in which you have objects acting at least quasi-classically. And I'm not finding that in this probability distribution. And then we sort of step back and say, well, what can we get from in terms of a picture of the world in quantum mechanics? And the answer is, well, I don't think it's going to be interpretation neutral. So there's this literature on what is called the interpretations of quantum mechanics, which I think is a misleading phrase because that suggests to some people like you've got some purely mathematical formalism that's not physically interpreted. And that's not at all what we have. What you get in your quantum mechanics courses is you learn how to apply the theory. You learn how to associate certain quantum states with certain kinds of preparation procedures, certain kinds of Hamiltonians with certain kinds of systems, and crucially calculate probabilities of outcomes of experiments. All of this is couched in operational terms. So there's this interpreted operational core of quantum mechanics, which I think is the only non-controversial part of quantum mechanics that we all accept is quantum mechanics. And that doesn't say anything at all about what's happening in between experiments. So if you want to say, do I get something like a classical picture of the world, then you're already from quantum mechanics, then what you're asking is you're already going along one of these programs that attempts to get a picture of what the world is like in quantum mechanics, what a quantum world might be like that goes beyond this operational core. And there, as we all know, there are different avenues of approach. There are, additional Beables theories or hidden variables theories, like the de Broglie-Bohm theory. And then you can ask, well, okay, under what circumstances do the Bohmian particles obey something like classical trajectories? And there are answers to that. Decoherence plays an important role. You can look at the dynamical collapse theories and say, well, once we figure out how to interpret these theories as describing a world, when is that world something like a classical world? Or on the variety and many worlds approaches, you're not trying to get something like a classical world. What you're trying to get is something like, a branching into quasi-classical domains, and we can answer with that. So all of these involve going beyond standard quantum mechanics. And I think that that's right. If we want to get a picture of what the world is like, either in the classical limit or outside of it.
Thanks. And we have a very nice comment also in the chat by Ajit Iqbal Singh. The negation of a truth is a more profound truth. This is from Parthasarathi. So this is how theories evolve over time. So probably there's not going to be an absolute truth, but we're going to change it, adding up the knowledge that we get all the time from maths, from physics, from philosophy, from experiments, from whichever way we observe the world. Paweł, what's your take on this?
Okay, I think I will be quick. You know, the first, well, hopefully. So first, of course, there is a question what we mean by the time scale, classical scale, or classical world, because of course it's a matter of scale. And Ivette already was telling about this relativistic effects, and of course there's in some sense it is classical, right? But at the same time there is something significant. So I would just focus on one aspect first, which is this classical world in our scale, like in a scale of us observers. So this is the everyday life we see, and these are tabletop experiments. And the basic, there are two measurement problems, and one is the small measurement problem, another is big measurement problem. And the small measurement problem seems to be almost solved, which is well how we get commutativity, or in other way around, how we get classical phase space or classical distributions, or yet another way is how we get cloning, possibility of cloning, right? And that's, from that perspective, it seems that the quantum mechanical development of quantum Darwinism and recently the spectrum broadcast structure seems to solve, at least conceptually, the story. But still, I have some question. I would be much more happy if we had on this whole field at least one example carefully done when you just monitor evolution of the position. So in the sense that you have a trajectory, you know, and you just see how it goes. I understand that it may be hard and difficult, but still I would be really happy to see whether there is no hidden, say, little traps there. There is only one or two papers on that, and they do not, I think what is needed there is to have some memoryless environment very carefully included. So this is, but it seems we are kind of at least partially satisfactory, and quantum mechanics somehow, how to say, manages to do it. But the other thing is this big measurement problem, which is of course the collapse problem, and the problem why we do not kind of how to say, why there is the selection of the results despite the unitarity axiom. And you know, obviously, well, today I learned about this perspective from the talk of Antoine Pilloy. But you know, always you have the fundamental problem that is the problem of predictive power of the theory. Complexity, predictive power, and descriptive power. These three elements should be kind of satisfactory, right? So basically it might happen that all possible extensions that we have, well, that we could cook up, might be so complex that you cannot use them. The other might be that the descriptive power may be good, but the predictive may be zero because you don't have access to this dark sector, the sector that would kind of be this dilation sector. So that would be like, that would be very nice because we have Bohmian theory and it is nice. But from the practical perspective, it might be, well, still not satisfactory, right? And this is and yet another question is, of course, is the question whether it does have anything to do directly with the gravity or not. And that touches the issue of relation between quantum and gravity. And you know, I don't know. I'm not specialist, actually. But the one thing that I remember is the David Deutsch paper, Foundation of Physics, 1986, when he comments on Wheeler paper. But the important point from the present discussion, I guess, and from this issue of reconciliation is the following. He says, when looking at ideal gas equation from 19th century perspective, you have temperature, pressure, and volume there. And if you try to somehow think in general terms, obviously all those concepts like pressure, volume, and temperature, and in that time perspective, they're very misleading. You wouldn't infer anything about the layer below. It's like, you cannot extrapolate it to get this, quantum statistics out of it, right? Mm-hmm. And so what I'm saying is that maybe if we ask about this relation, between quantum and gravity, maybe we should abandon thinking about generalizations of the formalist or one formalist or another formalist. Even GPT might be too little, because it somehow encodes non-commutativity. While non-commutativity may be kind of emergent feature from some mathematics that we don't know and we don't now even can imagine how it looks like. Thank you very much.
Thanks. That's very good food for thought. And
thank you very much.
Thanks, Ajit. Okay, Rob, it's your turn now.
Hey, thanks, Gerardo. Okay, so it seems to me that there's perhaps two primary reasons that people think that, or two primary types of evidence for the need of modifications to quantum theory in order to do justice to the classical limit in some way. So one I would say is, what motivates dynamical collapse theories. It's the measurement problem. It's Schrodinger's cat. The idea there being that there's certain states of cats that we don't see that quantum mechanics says are possible, and so how does it happen that we don't see these strange states? So on that front, personally, the way I see it is that so my answer to this question is that I don't think quantum theory needs modification. So on this particular case, I happen to believe that the quantum state doesn't represent reality, it represents our knowledge of reality. And so that's what went wrong with the Schrodinger cat argument, that these strange quantum states you can write down for cats are, according to this point of view, exotic ways of knowing about reality, not exotic ways of reality being. And so the classical limit looks very different when you take an epistemic view of quantum states rather than an ontic view of quantum states. The second reason that I see given is that we need to be able to recover from some putative theory of quantum gravity. We need to be able to recover general relativity in some limit. And thus far, we haven't made much progress, and therefore maybe the problem is that quantum theory needs to be modified. So there again, I don't see a need for modification because to my mind, as we saw a little bit of in David Schmidt's talk, that that there's a problem that I feel hasn't been solved with respect to quantum theory, which is what in the formalism of quantum theory really does represent causal structure and what is merely about our knowledge and about inference. And until you've got that omelet unscrambled properly, I don't think you have much of a chance of understanding how to unify quantum theory and general relativity, because general relativity is ultimately a theory about causal structure. So I'm not surprised that we haven't succeeded at unifying those theories yet, if we're fundamentally mistaken about what quantum theory is saying about causal structure. And then finally, I would say just that if you do take this sort of approach that I'm describing, I mean, it's the more interesting question is not transition to classicality, but more, or what is classicality to some extent? Like the question presumes a little bit that we all agree what classicality is, but if we have fundamental disagreements about what sort of category a quantum state is it something ontic or epistemic, then we may also have deep disagreements about what kinds of things even go classical, let alone, what the criterion for classicality is. So, from my perspective, both the theory of inference and the theory of causation can go classical, and we need to account for both of those things. And my notion of classicality happens to include a commitment to Leibniz's principle that if things are operationally indistinguishable, they should be ontologically the same. And what that leads to ultimately is that the boundary between non-classical and classical is basically the boundary between violating a Bell-type inequality and satisfying a Bell-type inequality, and more importantly, also the boundary between violating a non-contextuality inequality and satisfying one. And right now we don't. I mean, the non-contextuality inequalities have much broader scope because many more experiments can be cast as contextuality experiments than as Bell-type experiments. And so, now I feel like there's a big project to figure out, which aspects of a given quantum phenomena, whether it be state discrimination or cloning phenomena or teleportation or like any number of phenomena, what is it about that? What nuanced features of that phenomena show me that, I can't have a non-contextual model of that, which means I can't have one of these Leibnizian classical representations. So yeah, for me, that's sort of the frontier. We need to understand better which aspects of quantum phenomena really are indicative of non-classicality.
Thank you very much. Thanks all four of you. Right. I don't know. So there's no question yet in the chat, so I can probably proceed with some of the. I don't know. We have one just right now. Let's see. Okay, so fine. Let's read the question by Tulaprop. Standard approaches to open quantum systems, like master equation, trajectories, and so on, are deeply state-centric. At the same time, we say the coherence is the environment measuring the system, and measurements are naturally representable in state-independent ways, like Krauss operators, POVMs in the Heisenberg picture, at least for closed systems. Do you, and by you, I mean whoever wants to answer, do you believe the coherence is a physical property of the of quantum state itself, or is there some other way out of this?
I thought there's a question for Rob.
Not sure I've quite understood it. Is the coherence a physical property of the reified quantum state? It sounds like it's not
What's
a question.
the
I don't want to. So reify just means make real. I don't want to reify the quantum state. I want to epistemologize the quantum state. So this is a question more for you, Wayne, or perhaps for Ivette.
Or the reason I thought it was a question for you is one way to think of it is, well, how do you think of decoherence if it's not a property of the reified quantum state?
Well, okay, maybe I can answer that question very briefly and very generically, which is that if you take the view that quantum states are states of knowledge, then very broadly speaking, what's the transition from quantum to classical in relativity? It's about the speed of light. What is it in quantum theory? So what's the parameter? And I would say it's your degree of certainty, your degree of knowledge. If I have a lot of uncertainty about a system, it's going to look classical. Only in those situations where I have a lot of knowledge about a system can I expect to see violations of Bell inequalities or violations of non-contextuality inequalities. So quantum theory is a theory of the very certain. And if I have systems interacting with my system of interest and carrying away information about it, and I don't have knowledge of those systems, there are photons coming in from elsewhere, that tends to make, reduce my amount of knowledge about the system of interest. It tends to make it look classical.
I would like to make a comment, but I think it's going away a little bit from from that question, but it just made me be curious about something I want to ask to Rob. So that is the approaches that I'm familiar with on trying to reconcile quantum mechanics and general relativity are string theory, loop quantum gravity, and some other collapse of the wave function and many other approaches, but all seem to sort of assume that there's some reality in the wave function, right? When they try to build these kind of reconciliations. Do you know of any approach in which you consider more your point of view and then sort of try to connect with DR? Because I like when you said that, I thought like, yeah, I mean, I do think that what you say makes a lot of sense, but it's kind of, you know, because I've been always I'm very focused on experiment for many years now. So it's been really nice to come here and listen to like the more philosophical and the other end and so on. But I think that would be like a good attempt, is to take your point of view seriously and then see, okay, from given that, how would we then reconcile with general relativity? Could be an interesting approach.
Yeah, I think the answer is no. There aren't any approaches to quantum gravity like this. I would say they're not all psiontic approaches right now. Like I would say there's certain people who are pursuing kind of more operational approaches to quantum gravity, where they're trying to just be agnostic about questions like this.
But I think underlying to all of them is kind of thinking that the wave function actually is describing reality, no, in like the more like standard way.
I would say that, you know, for myself personally, I feel like, you know, when one needs to maybe sort out quantum mechanics before one engages in the project of unifying quantum theory with general relativity. So I don't feel the particular research program that, you know, I'm talking about has sorted it out.
We don't want to wait until you guys sort that out. I'm joking, but hopefully you'll do that very soon.
I don't know if you're able to read the questions from the chat, or if you'd like me to announce them. So there's a couple of new questions there. One is from Peter Morgan. We've been discussing about if we need to define what the classical word is, actually. So is classicality something more than just all measurements are compatible? Or in other words, does the classical algebra of measurements need to be commutative?
Paweł, this sounds like a question for you. Why don't you have a stab at it first?
Okay. I think at least this is some perspective that is kind of naturally assumed, right? That whenever you can boil down the analysis to some algebra that does commute. Well, all the questions that you are asking, right? So we are asking about the theory that is kind of that is enough to describe all the physical reality that we're trying to describe. That's the general, the kind of general, I think general, how to say, consensus. However, I've heard of recent results that are saying that you might consider something that is not naturally classical, yet you have some sort of say compatibility. Okay, I wouldn't say much more. From my perspective, the very natural is the situation when you have algebra that does commute, when you have measurements that do commute, and you have a classical space, probabilistic space. Yes. There is yet another very interesting question about reality itself, but I will comment on that later. Thank you.
Maybe I can add to that. Is that all right, Gerardo?
Yeah, so there's another question. Sorry, what did you say, Robert? You want to add?
I was going to add something to Paweł.
Oh, yes, please. Yeah, no, you don't need my moderation. Get going in your discussion.
So I thought I would just mention that, you know, what is classicality, you know, is controversial, and it really does depend on some of your interpretational commitments. I would say for people who take an operational approach to quantum theory, all measurements being compatible is the notion of classicality, or part of the notion of classicality that they endorse. So like in the generalized probabilistic theory framework that we've heard a lot about, you know, being classical means that your state space is a simplex and your measurement space is, you know, the hypercube that's dual to that simplex. And that means there exists a single measurement that can simulate all other measurements. That's what classicality is. But if you're pursuing a realist program, then I think that is not as natural a notion. And so from my perspective, the more interesting question is, could I take, like, if I have a theory that's characterized as a GPT, could I embed those state and effect spaces in a deeper theory which had a simplex for its state space and a hypercube for its NFX space. And what we showed recently is that, that sort of question, I haven't given you all the caveats, but that sort of question is equivalent to the question of, does it have a non-contextual model? So that's quite nice. If you say, oh, my notion of classicality is admitting of a non-contextual model, then it's about embeddability in simplex. And then it's not about commutativity of measurements. So for example, I have various toy theories where, the world is classical deep down, but there's a restriction on how much you know. Those theories have non-commutativity in them, but I would still say they're fundamentally classical in the sort of ontology they posit. Sometimes I talk about sort of weak and strong non-classicality. So weak non-classicality would be, well, it's classical except for the fact that you can't know everything, which is a very kind of mild sort of change on a classical world, to not be able to know everything. Strong non-classicality is when you're really violating a non-contextuality inequality or violating a Bell inequality, and you can't think of it as just limited information about some classical world.
Good. There are a couple of very interesting questions in the chat. I just want to ask one from the organizers list that I think would appeal to Wayne, because we haven't heard from Wayne in a while. So the question that we have, at least some of us have, is the following. Should fundamental theories contain words like observer or agent, or should this just actually dissolve in a good theory? Because, for instance, Newtonian gravity, electrodynamics, which were big successes at their time, they seem to make no reference to observers, but quantum mechanics and relativity, which also were big successes in the further time, do. So what's your take on this, Wayne?
Okay, yes, so as I think most people are familiar, Bell famously wrote this paper or rant called Against Measurement, where he proclaimed that fundamental physical theories or serious physical theories shouldn't contain words like observer or agent or measurement or apparatus or system and environment and stuff like that. I think that that's right. I think that something that has some pretension of being a comprehensive physical theory. Of course, we have yet to have anything that's really a candidate for that. But yeah, it shouldn't require those sorts of notions for their formulation. Now, as a matter of fact, quantum mechanics as standardly formulated does use some kind of, at some point talk about measurement or use some kind of apparatus system split. And of course, some of the work on quantum foundations is been to formulate a theory of the sort that Bell would want. That there's been a series of conferences called Quantum Mechanics Without Observers. So all of the major approaches to the so-called measurement program that I mentioned don't, be a hidden variables theory or dynamical collapse theory or an Everettian theory, don't require those kinds of notions for the formulation. That's good. I think that's right, and it's healthy. In the question, it said the special relativity requires observers for its formulation. I don't think that that's true. We shouldn't conflate frame dependence with observer dependence, even though, for ease of exposition, we imagine Alice on the train or on a spaceship or something like that, but it's got nothing to do with there being an observer, stuff like that. And also I think that relativistic theories are best formulated in a frame, in a frame independent way. The actual content is, it can be expressed without mentioning even reference frames. I just got finished writing a draft of a paper that I'm going to be delivering at the Philosophy of Science Association meeting coming up in early November, in which I argue that even though that's right, that theories should be capable of, a comprehensive physical theory should be capable of being formulated without these notions. It's also important that we be able to include such notions in it, and that the theory be capable of not describing all of reality. Because when we actually apply a theory, when it comes to hypothesis, statistical hypothesis testing or things like that, we treat the settings of the apparatus or something basically as exogenous parameters. We just say, okay, given this, what does the theory say the system is going to do? And we're not asking the theory to tell us about the process by which those settings get made. And when you apply causal notions, the notion of an intervention it involves involves treating certain parameters as exogenous. So I think that's important that the theory be capable of that kind of formulation. Otherwise, you end up, in a situation where you're taking superdeterminism seriously, and you say, well, okay, everything's fine and local as long as we let the initial conditions determine both the outcome of the experiment and the setting of the experiments. And I think that just makes nonsense of the way we actually apply and test physical theories.
Anything to add, or to disagree, or to enforce this point?
I think I look at the observer from different perspective, a little bit, I would say, maybe even a rebellion. That's the result of recent research that we did with Michał Eckstein on this. So basically, we realized that the problem of observer is actually inherent in any physical theory. Basically, you have an observer paradox that you have really pushed the observer outside. Because if the observer is a part of the model, then you cannot test the model. So Michał Eckstein took up the very elementary example in general relativity. So there is this global hyperbolic equations, right? And the true thing is that when you have on the hyperspace and you have the position, you have future and past, they are kind of determined by this layer. So when you consider just to observe your universe by the telescope, but you decide where you put your telescope, right? So would you put on Chile in South Africa? Actually, you build it somewhere. So you change the mass distribution. And of course, either you have to say, okay, it was all predetermined. I couldn't at that time, I couldn't look at that part of the sky because I was predetermined and everything was predetermined. Or if I was not, then actually from the perspective of global hyperbolicity, you kind of change the past. So in that sense, and this is, of course, we say, okay, this is the matter of scale, so it doesn't count much, right? But the question is when you destroy the comet that is passing by or not, and it was supposed to make the black holes to collide or not, then the issue becomes more substantial. So basically, in any theory, there is this kind of tension between observer that's supposed to be outside of the theory. It's supposed to have free will to test it rather than being inside. And even Michał Eckstein has even this point that he says that maybe that's the reason why there is no global theory like general unification, but there is local. There are theories that are locally consistent. So we have a paper on that. But why in quantum mechanics, it really is very exceptional. And it really is. So, the thing is that when you have the theory and you test it, then the observer that is supposed to test should have, in quotation marks, in a very vaguely way said, the same power as the theory does. And quantum mechanics says, okay, I have this ontological randomness, okay? So from that perspective, the observer should have something that is from outside and that is this ontological randomness, and we call it free will in Bell experiment, right? So in that sense, it's very drastically, he has to be uncorrelated from all the statistics that quantum mechanics predicts, and this is the reason why Bell experiment required that. So that's the reason why I think on the very fundamental layer, the observer has a special status. But there is yet another aspect, which is this commutativity versus non-commutativity and this collapse. And this is yet another issue, which is, okay, of course, you are invasive if you perform the relativistic experiment. But I would agree with what was said. Just it's not the same as in quantum mechanics because you are not at all invasive in the process of collecting data. Okay, while in quantum mechanics you have to be. Okay, and this is completely different. There are completely different aspects. And from that perspective, I would say the observer problem in quantum mechanics is a special one. And maybe any future theory that would try to reconcile, maybe completely different, might at some point, would have at some point stumble upon that. Thank you.
Thanks.
Paweł, could you send me a reference to that paper you were talking about?
Oh, yes, I would just put it in the chat, right? That's just will give you just the link is right. It's here.
Right.
I think it is it. Right.
Okay.
Thank you very much.
Any other views on this point?
No, I agree with Wayne and also, Paweł was saying that in general relativity, I don't think it's an issue at all. I mean, you can measure in the experiment that you have a clock here and the time ticks different from a satellite, but that really has nothing to do with, it's a reference frame and it's not it's not an observer because of what Paweł said, you're not interfering where you're taking the data. There is that's one of the interesting issues with quantum mechanics. And I guess Rob must say that I guess it's not a problem if you take the point of view that the wave function is not talking about reality. No, I suppose that would solve and take the observer out of quantum mechanics, or am I wrong about that?
I think I'm in agreement that a notion of observer as an unanalyzed concept, that doesn't belong in a theory, as if it's just some sort of primitive notion that we can't analyze any further. I agree that shouldn't be there. I mean, I would say that though, there are lots of different notions of fundamental. If you're talking about a fundamental theory, I think as physicists, we tend to think about sort of like a reductionist theory where somehow, you want an explanation that's just in terms of the most primitive elements. But those, the theories we have, the most useful theories we have can give us a lot of insight and be fundamental in other ways, even if we don't have that. So if I ask the analogous question about a fundamental theory of life, and I said, should a fundamental theory of life contains words like organism and replicator? Well, from one perspective, you might say, no, a fundamental theory of life should explain how replicators even came to exist in the universe. It shouldn't presume the existence of replicators. But we're not there yet. We don't understand the origin of life. And so if I want to give you lots of insights about our most fundamental theory of life, you have to give me the notion of replicator as something I can talk about, and we'll postpone the problem of explaining it. And I take a similar attitude towards observers and agents. Yes, we need to explain how it came, for example, if every observer in the universe can't know everything, we need to explain that in terms of the fundamental physics of how the observer is made and why is it that the physics is such that they can't know everything. But we can still postpone that problem for some time and talk about, what our best theory, quantum theory, tells us, about what observers can know and what kinds of interactions and interventions they can make and all those sorts of things. That's, I think, fair game for a physical theory.
Sounds about right. We have a question for everyone. I don't know who wants to answer. Has the preferred basis problem, as raised by Adrian Kent and others, been solved? Can you comment on its status? I don't know if we want to invite this person to elaborate. I don't know, Prem? Who's Prem from the audience?
Yeah, I'm not familiar with that.
I mean, I take it that this is a reference to the preferred basis problem in Everettian or many worlds type, interpretations of quantum mechanics, and the approach primarily favored by least in philosophy by people, those are the sort of complex of ideas that started coming out of Oxford in the 1990s and early O's, and looked to the phenomenon of decoherence to pick out, quasi-classical realms. So it's not that there's a precise preferred basis, but it's close enough. I think that that's okay. It serves the purposes that are needed for a theory like that.
Right, then we have a couple of questions from Farid to specific people in the panel. So question for Paweł, you mentioned the small measurement problem is basically nearly solved. If one takes Rob's epistemic view, doesn't your answer also imply refutation of the big measurement problem?
All right, I would say, as far as I was, referring to, it was just a question about quantum mechanics. So I would say I'm not sure whether ever quantum mechanics as a formalism would solve that problem by dilations. Methodologically, I'm stressing, in a methodologically satisfactory way, okay? I kind of explained what I meant, predictive power, complexity, and so on, okay? But if it goes beyond the quantum mechanics, this is a question to Rob. Actually, Rob, do you think that the issue of collapse problem can be on footing of your formalism eventually solved in a way that you would get, say, really the new time scales or physical time scales that would predict the things in the lab?
Paweł, I don't think I understood your question. Did you say collapse?
Sorry, Paweł, you're muted.
Sorry, the big measurement problem is a problem of collapse of the wave function.
Right.
So the question is whether your framework, okay, could lead to say practical, say new parameter that would eventually say, okay, I have a tabletop experiment and I actually know the time scale when it does happen and why it does happen.
Okay, well, so in the approach wherein you assume that the quantum state represents incomplete knowledge, you interpret the collapse of the wave function not as a dynamical process that occurs in the world at a particular time, but rather, the wave function is an agent's, it plays the role of like a probability distribution in a classical theory. It says this is what the agent knows. And when the agent acquires new information, like learning the outcome of some measurement, they might update their information about some distant system, like in the EPR experiment. I learn the outcome here and I update my information about what's going on over there. And that updating of information is described in the quantum formalism as writing down a new quantum state. And so, the suddenness of the collapse of the wave function is more about, there's a particular moment in my epistemological history where I learned that outcome. And that was the moment at which I was able to update my description and make better predictions about other things. But it's not a time scale for events to happen in the world.
Yes, that's true. But I understand that even phenomenologically, you may have a description that would say, during the evolution of experiment, right, you have the best possible knowledge of the observer. And this best possible knowledge does evolve somehow. So just on effective, footing. And I think then that the question about the scale is kind of justified. And do you think that your kind of formalism would add to some, say, effective evolution?
Well, like in this sort of approach, for example, unitary dynamics, yeah, maybe I can tie it into something you said earlier. Like in this sort of approach, there is no necessarily there doesn't have to be any objective stochasticity. So unitary evolution could be a totally deterministic dynamics, and it just involves like what I know about is changing. But I guess I'm still not clear on sort of what kind of time scale, like what's the phenomena for which you're looking for prediction
so
about
basically. Right. So basically, if the collapse is some moment when the physical parameters are such and such, or the physical properties are such and such.
Uh-huh.
Even if you don't say fundamentally, you may say, okay, in your theory, you might have dynamical theory that would say what is the maximum knowledge of the observer at a different time scale of the experiment, decade and a half, and then
I see.
collapse is fully justified. Of that knowledge, right? You know what I'm saying?
I don't think I do, but
From your perspective,
let me see. Let me see. Like, if one asked, are there kind of maybe fundamental limitations on how much an observer could know about timing, for example? I think, yeah, like there's, for example, the complementarity between energy and time means that if I do want to learn the time of an event very precisely, I need a lot of energy to do that, a big spread in an energy variable. And if the spread in the energy variable is so big that I expect a black hole to form, then I can't learn that time scale to that precision.
Sure,
so
but I'm asking about your theory. I know about quantum mechanics. I'm asking about whether your perspective could contribute to that, type of limitations that are, especially would say something about what we call in quantum mechanics time of collapse.
Yeah, I don't think so. I mean, I'll clarify that, much of what we're trying to do is just an interpretational program of like take the quantum formalism with its predictions and try to understand and unscramble the omelet for it. I mean, it may indeed have different predictions for, things we don't know how to do now, like quantized gravity, or, how do we do causal inference in a quantum world? There's machine learning. There's lots of cases where I think there's disagreement about how to apply the quantum formalism. So there's opportunities for new types of progress. But roughly speaking, like for all the experiments that involve dynamical collapse, this approach says you're not going to see any anomalous decoherence. The world is evolving unitarily.
Fair enough. Thank you.
Yeah. So there's a very nice question from Dan, which I think we can take rounds in answering as we're getting close to the end time, unfortunately. Yeah. So Ivette mentioned at the beginning the role of experiments in determining actually progresses in foundations. Are there any experiments currently underway which would or could answer some of the foundational questions that are at the heart of what you do for each of you?
Thanks, Dan. By the way, I was feeling guilty before because I didn't say hi to Dan because he's also organizing. And thank you very much, Dan, for this invitation and organizing. And I'm looking forward to seeing you. I saw that there was a little D somewhere, so that might be him, no?
That's me. Hi.
Hi. Very nice to see you. Let's catch up soon.
You too. Excellent. Yes, thank you.
So so in the what concerns to my research, well, I think, in my opinion, the most important question to answer is if the gravitational field can be, space-time can be in a superposition of two different configurations. So for that, you need a massive system in a quantum superposition. So there's an experiment by Dick Barminster who is doing that with mirrors. And the typical, nano beats like what Angelo Bassi and Catarina did, that they spoke about it in the conference. And then there's Marcus Arndt, Henrik Ulrich, Gavin Morley, so many other people doing experiments with nano beats and nano systems like that. And there's also, I would say, the space experiments. You do have relativistic effects when it comes to, distances between the Earth and satellites and so on. So there are some aspects of the overlap of quantum mechanics and general relativity that you could test like that. And some of my own proposals in that direction are seeing if you can measure space-time using quantum systems like BC, will all fall into trying to put together some of the pieces of the puzzle with respect to understanding GR. And actually, there's so many other experiments that are coming to my mind. Also, some experiments by Chris Westbrook with mass and entanglement, and Philippe Boyer entangling massive systems in larger distances. I mean, there's quite a few experiments. Yeah.
Well, it looks like you have lots of chances to get what you want. But
yes,
they're hard ones, yeah?
Hopefully, yeah.
Good. Anyone else?
So if I may add, actually, these are very interesting directions. And I think everybody who is, interested in foundations is kind of waiting what these experiments would, Ivette were telling us about, would tell. I think there is one more possible perspective that is by far too difficult to even imagine these days, which is kind of trying to make quantum engineering experiments or quantum information inspired experiment at subnuclear scale. When you really try to have a very precise scattering of nucleus with very well prepared objects. So this at a very tuned energies, and this thing, I think I don't even know whether there will come day when people would be able to do that. I think it might give some insight, and that quantum information might contribute to understanding, or at least to some perspective on this region of physical scales. Thank you.
Yes, I agree. We have a couple more questions, actually. One is a follow-up from Peter Morgan. I don't know who wants to answer this. So commonly people add hidden variables to quantum mechanics to try to make it like classical mechanics. What happens if we instead add hidden observables to classical mechanics so that the measurement algebra becomes non-commutative? Is that enough change that all systems can be understood as classical?
Maybe I'll have a go at this. That it's not totally clear, but if I were to interpret adding hidden observables to classical mechanics, in very loosely, as maybe imagine that there's only some things you can observe and other things you can't observe, and so it sounds very much like an epistemic restriction to me. And you certainly do get non-commutativity in the sense that there's all your measurements are coarse-grained and you cannot implement them all simultaneously. So there's incompatibility. But no, you don't get all of quantum mechanics from that. What you miss are things like non-locality and contextuality.
Thank you. I would ask, well, I have two questions, but they would both require flash answers, let's say. One, I wanted to talk about the future, but let's make it time symmetric. What is, in your opinion, the most influential contribution in quantum foundations in the past decade, and what would be the most desirable one to achieve in the next decade? Take rounds.
The difficult one is the one in the past. That's why we're all thinking, because
we're all kind of going, okay, past decade, we're trying to remember when certain things were being done. Like, we're yes.
Fine, you can relax the time scale if you like.
Yeah, I mean.
Okay, may I answer one thing? I think one thing that is very important was this closing space-time loophole in Bell experiment, right? That was definitely the thing that absolutely was, people were waiting for this for decades.
I agree. Yeah, that's certainly the most significant thing that's been done recently.
So just to make things interesting, I'm going to disagree, simply because I don't think the loopholes were very plausible, and so I don't think anyone really thought anything else would happen. But for me, I think one of the interesting things that's happened is the kind of resurgence of interesting work on Wigner-Friend type problems. So the Frauschiger-Renner result and results that came after that. I say that because I think those results have been really fruitful in the sense that they've made people in different interpretational camps refine their views and sort of clarify what they believe in response. So, which of the, it was a really nice no-go theorem after it was refined, because it has a bunch of assumptions, and then you have to say which of those assumptions do I want to give up, or which set of them do I want to give up. So I think it was really useful in terms of like moving the discussion forward about what different interpretations are committed to. And I also think it was really nice because it's something that I don't know how to address it. I don't know how to think about that problem. I have some ideas for how it might be resolved, but I really don't know. So yeah, for me it was really interesting.
Okay, may I just comment? So the issue you picked up is very interesting, but I understand that was a little bit tuned down. It started from the many words kind of interpretation support, right? And then during discussion, it was kind of clear that it doesn't go so far. But it was really very fruitful discussion. Even if people didn't agree, they each of the camps may step forward in understanding of the things. That's my impression. Yes, as far as experiment is concerned, I assert that at least the last experiment by Harald Weinfutter, the one that was 2 years after the three come out, it's already kind of convincing. And in that sense, I think from the broad perspective, it was a milestone, experimental milestone. So in that sense, whenever we understand science to be eventually falsified experimentally, that was kind of my justification to pick up that.
Thank you. Ivette?
So I'm thinking about when I learned quantum mechanics at university, and my teacher was saying that, quantum mechanics applied to very few particles, small, scales, and so on. It was also before, I shouldn't say that long because people are going to think like, what? But it was, before the big experiments from Harosh and Dave Wineland and things like that. Actually, my teacher loved the statistical interpretation of quantum mechanics, and he always say quantum mechanics only applies to ensembles, and we can't say anything about single particle experiments and things like that. So I was thinking about those times and now, and I think one of the things that have really caused a huge impression in me are really changing those views of what were the limits of quantum mechanics, and talking also about boundaries. Know that quantum mechanics applied to small scales, and now you can see that with these satellites, they can distribute entanglement over thousands of kilometers, and that you can have a BEC with, I don't know, in hydrogen 10 to the 10 atoms, and sodium 10 to the 8, 10 to the 9. So this notion of a few particles and small distances have really changed. Also, for example, Wineland's experiment where he can have a quantum clock and then move it just now within a centimeter and see time dilation. So all of these things have really blurred those lines on what are the scales of quantum mechanics and what are the scales of general relativity. And for me, that has caused like a great impression.
Yeah, that's a very nice consideration. Actually, you even mentioned about boundaries. And I was the one who actually proposed the name of this workshop, but now I'm thinking, reminding myself of the never-ending story where there's this line, Fantasia has no boundaries. Maybe the quantum world in the end has no boundaries, or at least there's still a lot of road ahead for us to be able to map them properly and find out what they even mean. So I think at this stage we have just slightly overrun the time. Unfortunately, it would be nice to keep discussing, but I think everybody has had a full day, and I would like to thank the 4 panelists a lot on behalf of myself and the organization and all the people who attended. Thank you so much. It was a lovely discussion. And at this stage, I would like to bring on the virtual stage Dan and TK, who were the driving force behind this workshop. And I personally want to thank them so much for actually making my job as co-organizer super easy, because they did everything. And so they should take the credit for the success of this workshop. So please, Dan, TK, closing words are on you. Thank you, everybody who attended and engaged in this workshop.
Thank you so much.
Thank you.
That's very kind of you, Gerardo. And thanks so much to the panelists and to everyone who's given a talk over the 2 days. Thanks to everyone who contributed questions and everyone who took part in the discussions. I've really, really enjoyed this, and it's been really fun to hear so many of my different interests within quantum foundations be in dialogue with one another and to be able to, the great thing about organizing conferences, you get to pick all of these very interesting people and invite them. So yeah, I've really had a great time, and thanks very much to everyone who participated.
Hi, everyone. First of all, I have to say that Gerardo lied. He definitely helped with the workshop, so everyone should also thank him. And also, yeah, I have to thank everyone who kind of signed up and gave a talk and all that, and received all of our emails and replied to them. And yeah, it was really great to hear everyone, and also it was really great to see everyone kind of discuss during question times and in the breakout sessions. And it was, I think, very fruitful for basically a lot of people. And yeah, thank you again.
Hope to see you all soon in person at the next event. Thank you very much. So
Thanks.
the workshop is closed.
Thank you very much.
Thank you very much. Very
Thank you.
nice seeing everyone.
Thanks.
Bye
See ya.
bye.